In this task, we're going to be taking a look at several sets of data and determining what type of function best models them. Up to this point, we've looked at some linear models, but now we're going to incorporate other functions that we've studied this year, including quadratic and exponential. Here we have 4 graphs where we're going to describe which function best models the data based on the shape of the graph, and then we're going to explain what the graph is trying to tell us in real life. In graph A, our x-axis has the average summer temperature, and our y-axis shows the crop yield. Which of our functions do you think best models this data based on the shape of the graph? Notice our graph increases. It seems to reach a peak and then decreases again. And so it seems to take on the shape of a parabola, which would make it a quadratic function. In this particular graph, as we look at the left side where our temperatures are cooler, our crop yields seem to be lower. The same thing is true as we look to the right of our graph. As it's hotter, our crop yields also appear to be lower. But as we take a look at that middle section, it appears that our crop yield is at its peak. In graph B, our x-axis is showing weeks after opening, and our y-axis is showing the number of visitors to a new store. Which type of function do you think best models this data? This one isn't as obvious as the first for many of us. Notice there are a couple of options that we could choose here. If you're just looking at the data through here, we may say that this is best modeled by a linear function. But if you look at the data from its beginning, you may notice a curve there, and so some of you may have decided that this is best modeled by exponential data or by an exponential function. Later in this video, we're going to look at some tools that would help us make a definite determination as to whether or not this data would best be modeled by a linear function or an exponential function. But for now, let's take a look at the scenario. As the store has been open for a longer amount of time, the number of visitors to that store tend to increase. In determining whether or not we think it's linear or exponential, you've got to consider, is that growth of visitors happening at a constant rate, or would you say that it's not constant? Usually, with a scenario like this, once someone's visited a store and they tell their friends and their family and those around them about it, more and more people tend to go. And instead of a linear pattern of growth, we're likely to see something more exponential. In graph C, on our x-axis, we're looking at the years starting in 1900 to the year 2020. And on our y-axis, we have the price of U.S. first-class stamps. Which of our functions do you think best models this data? As our years increase, notice the price of our stamps is increasing. What doesn't happen is that that increase is occurring at a constant rate, and so this appears to show some exponential growth. Finally, let's take a look at graph D. On our x-axis, we have age, and on our y-axis, we have sign legibility in feet. Which type of function do you think best models this data? Here, I would say of our choices, we're looking at a linear model. As one gets older and older, it appears that the farther away a sign is, the less legible it is for us to see. While the correlation here isn't as strong as some of the other examples, it does appear that we could find a line of best fit. When we are looking at nonlinear functions, we find best fit curves. And so in our next examples, we're going to be looking at finding those best fit lines and best fit curves using technology. In 3 of our examples, the shape of the data made it pretty obvious which type of function would best model the data. But what about example B? How would we know which of our models or which of our functions best models our data? What we are going to be taking a look at as we determine our regression models is our correlation of determination, and it is abbreviated using R squared. In the past, we've looked at correlation coefficients and determining the strength of the data being related together. Now we're going to look at the coefficients of determination. Our coefficients of determination tell us how much variation in the output is related to the changes in the inputs. As we compare our regression models in the next examples, the model with the highest value of R squared will be the best model to fit the data. In our first example, we have data of the population of the United States from 1880 to the year 2000. In order to make a scatter plot, I used a graphing calculator. I actually used the TI-84 that many of you have used in class. For each of these examples, I will show you the results of my scatter plot and my regression models. But if you're interested in trying it on your own, I'll include the directions of how to use the calculator in the module. Here you can see the scatter plot that I made on the calculator for U.S. population. As recommended in the directions, 1880 is 80 on the x-axis and 1890 is 90 on the x-axis, and so on and so forth as we go through the years. Which type of function do you think best models this data? We aren't going to answer that question just yet, but I do want you to describe the direction and strength of the correlation. Is it positive? Is it negative? Is it weak? Is it strong? Is it moderate? Do you see no correlation at all? Notice as our years are increasing, so is the population of the country. And so as our values on our x-axis are increasing, so are the values on our y-axis. Therefore, we've got a positive correlation. Here it appears that we have relatively constant or change that is happening within set parameters without huge outliers, and so I would say that correlation is relatively strong. In order to determine which of our functions best models our data, we must look at the regression models for linear, exponential, and quadratic and compare their coefficients of determination. I was able to use the graphing calculator as well to find each of our equations. Here we have our linear regression model. Notice when we get that equation from the calculator, it doesn't just put it all together for us. We have to substitute the values in. Notice also here we have both an R squared and an R for linear regression. That R squared is our coefficient of determination that we're going to be comparing with the other models. And the R is our correlation coefficient, showing us the strength and direction of our correlation. Now let's take a look at our exponential model. Again, you see here what our general form of our equation is, where we have to substitute in those values that we got for our regression model. You have your correlation or your coefficient of determination as well as a correlation coefficient, but we're taking a look at that coefficient of determination. So far, as we compare the two models that we have, because our coefficient of determination for our exponential model is higher, some of us picked linear at the beginning, but it's looking more exponential. We're not done yet though, because we have to take a look at our quadratic model. Based on our regression models, it appears that our quadratic model is the best fit for this data. We're going to use that model to make a prediction for the U.S. population in 2015. Go ahead and see how many people you think there were in the U.S. based on our model. Hopefully you were careful and did not substitute in 2015 for X. Remember, we started counting at 80 for the year 1880. And so what we want to substitute in for our X is 215. So using our model, we'd expect about 323.4 million people in the U.S. in the year 2015. Since that year's already passed, you could always go back and look to see how accurate that model is. Remember, as we're doing each of these, this is simply a model of the data. It doesn't mean that it's going to give us an exact answer that's accurate to what actually happens at that time. Let's take a look at one more example before you try this on your own. This time, we're looking at the U.S. Department of Health and Human Services as they characterize adults as overweight based on their height. Again, I've made a scatter plot for us to analyze. When you see that scatter plot, I want you to describe the direction and strength of the correlation and decide which of our functions you think best models the data. Notice that each of our heights is measured in inches. Our weight is measured in pounds. As we look at the data given, again, we're not going to determine which of our model or which of our functions is the best model until we compare those coefficient of determinations, but we are going to take a look at correlation. Again, as our x's increase, so do our y's. So as our weights are increasing, so are our heights. Or our heights are increasing, so are our weights, but they both increase. So that could have gone either way. And so again, we're looking at positive correlation, and it appears to be relatively strong. Now we're going to decide if your choice for which type of function is correct based on the data. Many of us looked at this graph and just knew that this data was going to be linear. As we compare our linear and exponential models, that linear coefficient of determination is higher, although only slightly. But then we get to the quadratic model, which is slightly higher than the linear. And so in the case of the data presented, the quadratic model would be the best fit for this data. We're going to use that model to predict the weight that would be considered overweight for a person who is 5'3". Go ahead and make your prediction. Remember, the heights in our data are measured in inches, so do that conversion first. So someone that's 5'3", who would be 63 inches tall, would be considered overweight by this model at 163 pounds. Now you're going to have some data to analyze on your own in their practice section.